I'm also Professor Chris Curtis from Math and Stats. If you don't know me, I know we have a lot of new folks from the CSRC. It's kind of early in the semester. So anyway, thank you for coming. We have from UC Irvine, Professor John Lowengrub. And I apologize, I forgot I was supposed to introduce you. So I do not have your CV memorized at the top of my head. However, that said, I've had to read enough of your papers and work with your material off and on over the years. John is a those like singular talents in applied mathematics that has been able to move across a number of unquestionably challenging areas, starting in, I guess, probably fluids is kind of how I know you, but a very mathematically sophisticated version of fluid mechanics. And then at some point, you just seem to kind of naturally jump over to math bio and become a leader in that. About what year did you kind of make that?
About 2000, 2001. So it's been hard to believe, 25 years, something like that.
Wow. Okay. And so if you go chase down, as I've had to trying to start work with John through mutual student Shivani, most of the biological collaborators on your paper are from, incidental places like Harvard Med and just these, regional sorts of institutions of one type or another. No, so really, we're very lucky to have John here. The work is, I've already read the paper, it's fantastic. And I think you're really going to enjoy it. So please, let's welcome John.
Yeah, thanks, Chris. Yeah, thanks so much for inviting me. I'm happy to come down. I've been here before, but maybe 10 years ago or something. You can't quite remember when I was back down, but it's a pleasure to be here. And regarding Harvard, it's one of the few times I'm happy I'm not at Harvard. So, although UC, we're going to have probably our own trouble, but UC Irvine is so far out of the fray. So I want to talk to you today about a problem we've been working on over the last few years, which has to do with basically doing scientific machine learning, but specifically for inverse problems and PDE inverse problems, and trying to learn parameters and equations from data. And so this is joint work with a number of different people. So I'm going to talk about two types of projects. One where we're more a biomedical application. And so we're looking at brain tumors, so glioblastoma, GBM. And this led us to a new direction, which we call BiLO, which is Bilevel Optimization and Local Operator Learning. And this is a project that was led by a former postdoc of mine, Ray Zhang, who just got a faculty position at Worcester Polytechnic Institute. And then this first problem is joint with a number of different people, led by Bjorn Mense at the University of Zurich and his group. But interestingly, the project was started by a high school student. And the high school student was taking classes at UCI and wanted to do a research project. And so I suggested something like this. I thought it would be doing, let's say, solving PDEs using neural networks. I thought would be a nice direction. And then that led to this whole area. On the BiLO, this is a joint work with Xiaowei Shi, who's in computer science at Irvine, and Chris Miles, who was at UC Irvine, but just recently moved to University of Utah. And so basically, what we want to do is learn, so when we're solving these scientific questions, we want to give mechanistic insight. That's my goal as a mathematician, to give mechanistic insight to the processes that are going on. So biological processes, for example, that's what we're focusing on here. And so the problem with these systems is that the data is limited. And so the data doesn't contain enough information that you would get, let's say just an image. Not enough information for you to really be able to say what's going on. And so we want to use the mathematical model to bridge that gap and provide a mechanistic interpretation of what's going on. And so these are examples of questions that one can address using PDE type models. One is glioblastoma. That's the main one we're going to look at. And there the question, so this is this very severe brain tumor. I'll tell you more about it in a few minutes. But the real question is how far do the tumor cells infiltrate the normal brain? And that's important because when a patient comes in for treatment, the doctors have to know, well, how much can they remove? So that's called resection. And where should they irradiate? And so what's standard is to irradiate a large sphere, let's say, around the tumor, but that also hits a lot of normal tissue. So one doesn't really want to do that, or at least limit that as much as one can. In Alzheimer's, there what we're tracking is not cells, but proteins and misfolded proteins. And again, one can use mathematical models to kind of predict how those proteins are distributed throughout the brain, and that is important for understanding the disease progression. And so here the question is, how do they accumulate or how are they transported? Another question is looking at basically gene expression and asking, so these are individual cells and these are RNA. And then the question is, well, these messenger RNA, they're going to be important for transcription. And so the fundamental question here is, how are genes transcribed? And again, one can develop mathematical models for all of these that involve inverse problems. And why machine learning? Why scientific machine learning? Well, from one point of view, you can't be totally data-driven because there's not enough data. The data is too sparse. Even though it looks like a lot of data, you have a lot of pixels. But for example, in these GBM, we don't have time data. And so the amount is really quite limited. So just regular machine learning would be very hard to do these problems, although one can do classification and that kind of stuff, but it doesn't really give you prognosis. Another question is, at least from the point of view of machine learning, is you need to interpret because you have to understand what's going on. And then fundamentally that understanding, we think, should come from mathematical models, and that's the bridge. And so that's the scientific part of machine learning. Now, why machine learning as opposed to traditional numerical methods for these kind of problems? Hopefully I'll convince you as we go through the talk that they provide a lot of flexibility that traditional approaches wouldn't do. And so that enables us to take advantage of a lot of the, let's say, the infrastructure been developed for machine learning, but now applying it to scientific applications. Okay, but what are the challenges? So, well, we have to, we have a bunch of data, and we have the PDE. And so we're ultimately trying to solve the inverse problem, which is determining parameters in the PDE so that you can fit the data as best you can. And, well, the data is noisy, so that's a problem. The model may not be correct, or likely is not correct. In this language, you would say misspecified. It contains the best, or at least some information that you can, but it's not going to be capturing the full processes. Just it's not feasible to do so. And then when you're actually trying to solve this problem, if you have soft PDE constraints, there's always going to be a trade-off between fitting the data and solving the PDE. Namely, if the PDE if there's a constraint saying that you want to minimize, the energy you want to minimize or cost function you want to minimize, if the PDE, solving the PDE is part of that cost function, you could balance between whether you fit data or solve the PDE. And if you're fitting data, you're not using the mechanistic equation. In addition, since the data is noisy, you want to be able to handle that, and the data may also be incomplete. So you may only be observing some of it, but not, you have latent things that you can't observe, latent variables or latent quantities you can't observe. And so you want to understand how that uncertainty passes through to your prediction and quantify the uncertain predictions that the models will make. And so that's important when you need to do what's called risk-aware decision making. You want to make sure that your system won't fail you're outside the range, and then of course uncertainty quantification is much more computationally expensive than this point estimate. Another challenge is that every time you acquire new data, so a new modality, then you may want to update the model to account for that new data. And so at the same time, you need flexibility. And so you want to be able to quickly adapt to new data and new model. And so that's the flexibility of machine learning. So the outline of the talk is going to be as follows. So first, I'm going to talk about solving inverse problems. And I'll use this GBM as an example with just what's more standard form of what's called a physics-informed neural network. And then we'll see that these trade-offs come in. So there's a trade-off between fitting the data and solving the PDE, how data, basically uncertainty is propagated, and then how we can change if we have additional data, then how can we change the model? I'm mainly going to be focused on this part, and we can do all of this within this framework of Bilevel Local Operator Learning, BiLO. So to start, let's calibrate models to data. So basically, this is a PDE constrained optimization problem. So we have a bunch of data and we want to minimize the difference between our solution of our PDE and that data. And then we want to, and I should have had that this is a function of data, we want to minimize over theta the parameters. And so you can think of this as the PDE is providing a regularization of the data. That's another way to think about it. But in any case, we have this constraint problem. And there's been a number of ways that one can address these problems. So traditionally, what are called adjoint methods, which are more traditional PDE type approaches. There's a neural operator approach where you're trying to learn a solution map from parameters to solution. And then the physics-informed neural networks, where I'll tend to focus on here. And so for the adjoint equation, basically you have to solve a forward equation and a backward equation, and this gives you a strong a PDE constraint because now you're solving both the forward and adjoint equation. And so then what you want to do is you want to do gradient descent, and so you want to be able to get an accurate approximation of the derivative with respect to parameters of your cost function. And so to do that within this framework, you have to do that with knowing the solution U, which solves the forward problem, and then this operator lambda star, and taking the gradient of that. So you have to solve the adjoint equation. And so you need to first, with this approach, you have to first derive the adjoint equation and solve it together with the forward problem. So you have to do both of those pieces of work. And so it's good, but it's expensive. And you also tend to have to regularize because the problems are not so well posed. For neural operators, I mentioned what you're doing is you're learning the solution, the map from parameters to solution. And so you do that with a bunch of synthetic data. So you have to do a bunch of pre-training. So you're going to generate these numerical solutions, and then you have a neural network representation where the W are the weights in the neural network, and you want to minimize over all of the data so that your neural network is matching your data for basically whatever parameters in this simple case that you've chosen. And once you have this, you can get it's basically can be used as a surrogate model. And so you can, neural networks, one of their advantages is they're very fast to evaluate. So you can, now once you've done this, you can think that you're solving whatever PDE you generated this data very quickly. But the problem is that if the parameter is out of the distribution where you trained it, then the solution is not very good. The accuracy degrades. Okay. Whoop. There we go. And examples of this are the what are called deep neural network, the deep learning operator network, Fourier neural operator and contact and so on. And so several references here. Physics-informed neural networks, these are a little bit different. So here what you have is basically layers of neurons, and often two, but you could do it, make them deeper. And then as inputs, you have your spatial position, space and time. Just think of that as your inputs to the network. And then the connections between the networks, that's the weight matrix for your neuron. And so then all of this is then put back together into a solution U. And then what you do for that solution is you use automatic differentiation, calculate all the derivatives that you need. So for example, if you want to use this to solve the heat equation, then you would calculate time derivatives, second derivative in space, and look at the residual. And that would be the loss, that the magnitude of this, let's say L2, would be the loss associated with the PDE. But you also want your solution to match data. So you have another component of the loss that matches the, for where you're trying to match the data. And so you put them together, and then you're going to minimize. And if you want to minimize, if you want to solve a forward problem, you would just minimize over the weights. But if you want to solve an inverse problem, like determine the D to match this data, you could also include that and minimize over that coefficient. So from that point of view, these guys solve the forward and backward problem at the same time. And they're mesh free, and the loss function is very flexible. You can just keep adding whatever terms you want. And so really what you're doing is you're solving the PDE, fitting the data, and inferring the parameters all at the same time. That was the striking thing about this approach. And so basically the solution we can represent from the neural network. If it's a neural network guy, we'll make it depend on W, the weights. And really what you were doing is we've converted that constrained PDE optimization problem into this unconstrained problem, where we're minimizing over the parameters and the weights of the residual. So that's how well you're solving the PDE, and how the data loss, how well you're matching the data. So now we have these two components, so we have to introduce a weight, W data, which is how much we're weighting the solution to match the data. So if W data is very big, then this term would tend to be dominant, and you could minimize the energy or minimize the cost by making this part small, but not necessarily making that part small. And that's the kind of trade-off. And so the residual is basically just how well you're satisfying the PDE. And the data loss is how well you're matching the data. And you're doing it over a different set of points. So the residual is a set of points you're putting down. It's match free, but you get to choose those points. And then the data loss, that's at the points where you have data. Okay. And so as next, I'll show you how we can use that to predict basically cell density in GBM, or how far the cells will will move. And so this is just an example. We can solve the problem in an actual image of a patient's brain, and these are the just an example solution showing the inner core of the tumor and the outer edge of the infiltrating cells. And so just a little bit about GBM. So this is the most common but most severe form of brain cancer. It's highly infiltrative, it's highly vascularized, and but nevertheless, there's a lot of regions of hypoxia. So it's very, it tends to not have a nice border. The cells tend to invade the normal brain. And the problem is, well, the challenges here are that the infiltration is anisotropic, because the brain has both white and gray matter, and cells move differently in those regions. The brain anatomy is highly patient specific, and nearly all patients have recurrence. So when it's treated by removal and chemotherapy and radiotherapy, nearly all patients have eventually succumb to the disease. I think the average, so basically after 5 years, only 5% patients survive. and the average amount of time between diagnosis and death is on the order of 1 year. So it's really a severe disease. And so the problem is you want to estimate how far the cells infiltrate, but you can't see it from the medical image because the resolution of the medical image is limited. So instead, and then you would irradiate that region where you think you have cell. So because you can't see it, the clinical target volume where radiologists would target the radiation, they take basically a large region around the tumor, and they just irradiate that whole region. And so a lot of normal brain is irradiated as well. And so these are some of the types of standard imaging, at least the first two on the left, that one can get from as the standard of care. And so this is a MRI, so magnetoresonance imaging. This is FLAIR. So this is measuring basically water, and it's lights bright because it's has a dye in it that patients would take, and then where the blood vessels perfuse that in the brain, this is where you'll see the signal. This T1 gadolinium, this is the region of active cells. And so you can see inside, so this is the whole big region, but we don't know how many cells are actually out here. Here, these are the cells that are at least we think to be active. Inside, it's dark because those are inactive, and that's what we would call the necrotic core. And then this is a PET image. It's a metabolic image, and this is not generally available. It's a very expensive image to get, and it has lower resolution than these two, but this is where the cells are metabolically active. And so the real key is only part of the tumor. There's missing data. Part of the tumor is not visible from the images because of the limits in resolution, and only one time point is typically available. Yeah.
But what do you gain from this image?
You gain, so between the combination of these two, you gain inside, you know where the necrotic core is, or at least where the presumably where the cell densities are highest but not active. And this is predicting that, well, the maximum kind of tumor extent may be here, but we don't know if there are cells here, and we don't know if there are cells here that we just don't see.
I mean the last one.
Oh, this one. Oh, so this one is, for example, is thought to be proportional to cell density. These are more thresholded. So these are saying, well, where the density is high enough, then the system will light up. But this is supposed to give you more information about the actual density. It's really metabolic. It's more like division rate, but that can be proportional to density. Yeah, there we go. Should have turned that, put all that there. Okay. Oops. So what one can do is then essentially do the segmentation. And so this is the segmentation of the whole tumor, some more of the T1 type together with some type of T2. And then this is the outer part, that's the flare. And so this you can get from a pathologist. And then the clinical target volume is all of this region around it, basically a 2 centimeter radius around the tumor. And then you can see there's a hole, and so what's happened is that the tumor has been removed from the hole, and then this is after some time, and I'm not sure the time between here and here, but the tumor recurs, and then this is the kind of distribution you would see again from the flare. And then the question is this real actually, or is that so? In other words, are there tumor cells there, or is it just, for example, edema or liquid that's come because you damaged the brain? Okay, so now let's use this information to build a patient-specific model. And so we'll do a very simple, because the problem is complicated, we start very simple. And so the simple equation is a reaction diffusion equation where there's diffusion. But now we'll have a variable diffusion coefficient because the diffusion in white matter and gray matter is different. And so that can be encoded in the P, which is essentially the probability of white matter or gray matter. And then a standard logistic term for cell growth or cell division. And so what this general system does is sort of supports traveling waves and weight and cell spreading. And then at the edge of the brain, there's a Neumann boundary condition. So the cells can't leave the skull. And so here U is the normalized cell density, rho is the division rate, D is the diffusion coefficient, and P is the distribution saying whether you're in white matter or gray matter. And then this D is the relative rate, basically ratio of the transport rates in white and gray matter. And then this is just a typical spatial distribution.
But you're assuming that the D is constant.
D is constant in each region, but we don't know the constant. We know the ratio. But... Okay, and so now we have to connect it with the images. So here's our predicted tumor cell density or concentration. And then this is the data. And so the data is, again, this just in terms of the MRI images, these are what you would get from the image, and then this is the corresponding segmentations. And so here we've segmented including the necrotic core, so that's why this region is bigger than this, just thin range. And then the connection between these two is the idea that, well, this MRI data is really thresholded. So what we see on the outside, for example, this white region should be, or let's start with the pink region. So the pink region is where should be where the cell density is high. And so we imagine that there's a threshold above which we're going to see things light up in the pink region, and there's that threshold UC-TC. And then for this flare region, we're imagining, well, that's where the tumor cell density is above some lower threshold. And then we have this WWT. But we don't know these guys. We're going to have to determine those. And then from these, if we just threshold, then we can get a predicted segmentation, and then we want to compare the two segmentation. And then we want to infer the patient-specific parameters. So we want to infer the diffusion coefficient, or the ratio of diffusion coefficients, the proliferation rate, and also the location of where the tumor is, as well as these thresholding parameters. And then we want to do that so that they approximate the medical scans, and now those are the segmented scans. And so what are the challenges? Well, we don't know the time, right? We don't know when the patient was observed. There's no ground truth. The data is noisy. And there's errors in the modeling. That model is very simple. And so a number of people have worked on this from the point of view of adjoint methods using PDE constrained optimization, Bayesian methods, so doing basically estimating ranges of parameters or distributions of parameters, and then looking at uncertainty quantification, how those propagate through, as well as machine learning approaches, and then pins. And so this is the how the whole system works with the pins. So basically, we have these various medical images. We get a 3D reconstruction of the tumor. We have our tumor growth model and our segmentations and our parameters. So essentially, the diffusion coefficient, the proliferation rate, and the location, as well as these thresholding parameters. So then the idea is, well, we're going to, these are all our thetas. And then we'll plug in the neural network. Well, so we have a bunch of weights. We have calculate our derivatives, calculate the residual loss of this, threshold, and then try to match. And then that's our residual loss and the thresholded solutions matching the y's. That's our data loss. And so this is an example of predicting our prediction of what this brain tumor, the cell distribution in this brain tumor looks like. And then if we put the numerical segmentations here, those are shown here. And then we can compute dice scores, so essentially how well the images are matching. And then we can say within this range of, let's say 1% cell density, how much does that cover the recurrence regime? And that could be the recurrence domain. And that can, if it's 1, it's covering it completely. And so that's a measure we can call efficiency, that basically the recurrence is occurring where we predicted the cells would be. Okay, so how do you actually do this? So you have a loss function, that's the residual, the segmentation loss, and then in addition to that, a loss because we want to constrain the parameters in a physical range. And then the idea is using synthetic data, we can try to estimate the weights. So this is like our data loss weight. And so we estimated that by solving a bunch of synthetic problems and seeing what works best, but we don't really know. And so here's an outcome. So this is the result from looking at a patient's tumor. And so the segmentation, again, those are what we saw before. But now there's solid and dashed. The dashed are the corresponding segmentations, or at least contours, corresponding to the values, the threshold values we found using the pin. Using the pin, we also found the parameters. So we can take those parameters and we can actually stick them in a finite difference method solving the same problem. And that's the solid. And what you can see is that while they're close, at least for the red region, so the inner core of the tumor, they tend to get farther apart the further away you go from the core. And so what did this tell you? This tells you, well, you use the pin to get this framework, pin framework to get the parameters. But in fact, the pin solution you get with those parameters is not matching the finite difference solution. So you're actually solving a different problem, not the PDE you're thinking you're solving. And what the pin is trying to do, because of this soft constraint with the weights, is trying to balance between fitting the data and solving the PDE. So if we change this data weight, we'll change the pin solution. If we make the data weight small, the two solutions will agree, the pin and the finite difference will agree, but they won't match the data variable. And but nevertheless, you can use, so you can, the parameters still are pretty good, and you can use them to estimate basically a personalized clinical target volume. That's this blue region, let's say 1% tumor, and you can do better than the standard clinical target volume. In other words, capturing the cells and the recurrence region without harming as much healthy tissue. Okay, so we've done this for a bunch of different patients, and it takes about an hour to do this per patient. We'd like to get it faster. You can do about a 30% improvement in the predictions, basically, compared to what has been done previously. And you don't need the PET-FET. You don't need this metabolic map, which had been needed previously in order to get better estimates of cell densities. Okay, but the key thing here for me is to say that what there really is a trade-off between solving the PDE and fitting the data. So how can you get around that? And we can try to get around it with this bilevel optimization idea. BiLO. And so here's the problem again, the PDE constraint. So we're converting it back again to a simple PDE problem. Our PDE constraint optimization. So again, to remind you, U is the solution of our PDE, and U hat is the data. And we want to minimize this difference with respect to the PDE parameters. So For PIN, the problem is there's weight of the data. And so there's a trade-off between you can minimize the total residual by basically reducing this loss. If this were very big, reducing this loss, fitting the data rather than the PDE. And in particular, if this parameter is very big, you're overfitting the data and you're not solving the PDE. And the other way, you're underfitting the data, you don't match the data, and so therefore you can solve the PDE, but your PDE parameters are inaccurate. And another problem is that really actually in the pins, the this data loss doesn't explicitly depend on the parameters. It's only implicit through the solution. So, and so in particular, just as I mentioned, the theta is updated if you do gradient optimization, the theta is updated by the gradient of the residual. There's this gradient of this guy, 0. And so this is the essentially the typical gradient descent of this type of problem. And so we're interested in doing a better job in this guy, incorporating that. And so suppose you know the PDE. So you know all the parameters. So then here is, this is the solution on the y-axis. So this shaded region. This is x, and these are the parameters. So for each set of parameters, our solution is a map that goes this way. And suppose our data are these red dots. And so what we want to do, if we started at some initial guess, we want to move down the gradient so that our solution is going to match these red dots. And so really what you want to do is from a particular, so at your loss, this is the loss as a function of parameters. You're starting here at some guess, and what you want to do is move along this curve so that you get to the minimum. And so you do that by gradient descent. You have to calculate the gradient.
But this is sort of like a Pareto front.
It's just the solution and a particular parameter.
No, but you have the loss of the data with the W is the sum of those two things. Right?
That yes, at the for the PIN. Yeah, but this one we're not going to do it. So but really what you need is you need the solution only if you want to calculate the gradient, you don't need the solution everywhere, you just need the solution locally. And so, well, one way of doing that is saying, suppose you have a residual, which is how much you're, basically how well you're satisfied with PDE. Well, then if you take the derivative of the residual with respect to parameters, that should also be 0. And so that means that you can solve the PDE, you should be solving the PDE just in a small region around where you are. And so one can introduce a gradient loss, the residual gradient loss, so you can define the residual as how well you're satisfying this PDE. And then you can take the gradient with respect to parameters and introduce a residual loss. And then the idea is that we can train a local PDE solution operator by minimizing this, so U is our solution of our neural network, but now inputs are X and theta both together. And so then what you want to do is minimize this combination of residual and the residual gradient. It's true there's a parameter here, but we find the results are not too sensitive to that parameter. And so if you do this, if you're able to minimize this, then you've actually solved, the neural network is solving the PDE in the neighborhood of the parameter theta. And so this leads you to this bilevel local operator learning. So we can take our PDE constrained optimization problem. So we were going to minimize the loss with respect to parameters, and that's our solution. Those are our parameters theta. Instead, we can convert it to a bilevel optimization problem. At the lower level, what are we going to do? We're going to minimize for a fixed set of parameters. we're going to minimize the residual and gradient to the residual. And so we're going to minimize over the weights. And that'll give us an optimal weight, which is now a function of theta. And then what we want to do at the upper level is we want to minimize over the thetas. And so that will give us our optimal guide. So that's basically, we can convert this guy to this guy. And so how do we actually do it? So we input our allocation points in our initial guess, and we do a pre-training. So we want to solve the equation at some parameter at this value. And then we're going to fine tune. And what we do is we do that by actually a simultaneous gradient descent. So in other words, what we do actually in the code is a little bit different than this, but this is essentially the idea. We use an add-on optimizer, but it's like this. So we calculate the gradient of the data loss, which now depends on both theta and W, and update the theta, and we update the weights by this guy. And so this is a simultaneous gradient descent. In principle, we should mix these two, but we do it this way because it's much cheaper. But it actually works. And you can show that actually computing the approximate, if you want to compute the gradient, you really should be computing the dW d theta here. But we don't calculate that. And so, but you can show that that's zero under some simplifying assumptions. And so the idea is now, compared to the previous approach of PIN, we didn't have parameters that were input to the system. Now we have these parameters, both the collocation points as well as the parameters being input to the system. And now we get something that explicitly depends on the parameters. And then at these intermediate layers, this is how you construct the solution to each layer. And you're training the W and the B, but not the R. And so you can construct the neural net. And so let's show you, let me show you how this works. So the first thing so let's look at the simple 1D Fisher KPP equation. So we're going to train it with diffusion coefficient 1 and proliferation rate 1. And that's our blue curve. And now what we'll do is we'll say, and so in this case, the solid is the neural network, and the dashed is the finite difference method. And so what I'm going to show you is, well, we trained it, and so that both the finite difference method and the neural network match at this value, essentially by construction. But now what we do is, let's vary the proliferation rate a little bit. And so we can then evaluate that neural network at this slightly different proliferation rate where we didn't train it. And we get this guy. And if we evaluate the finite difference method at that rate, we get the dash. So they're reasonably close. If we vary the diffusion coefficient, so we evaluate the neural network at this new diffusion coefficient where it wasn't trained, and we evaluate the finite difference guy here, they are also matching quite well. And so what this is suggesting is that by including this residual gradient loss, or gradient residual loss, that we can solve the neural network is giving you an approximation not at your parameter value, specific parameter value you trained it at, but nearby. Okay, and so now we can use this to infer diffusion coefficients. And so here again, we're giving as initial guess 1 like we did before, but the ground truth data, which is these dots, which are data with noise at these specific locations, they correspond to a ground truth problem where they're both 2. And so when you run this, you have the neural network in yellow, the finite difference method in purple, dash, and you see those two overlap very well. the ground truth solution is here. There was a bunch of noise, so you don't quite get the ground truth, but the point is that the neural net and the finite difference method match, and that the coefficients are pretty close. Okay. And so you get both an accurate PDE solution and accurate parameters, at least reasonably accurate. And then you can see that this does indeed go to it follows a gradient descent type behavior to the exact solution. And so then one thing I want to do is just, okay, let's see how well PIN does on this. And so if we increase the weight of the data, then what we can go is so if we're, let's say over here, so our weight of the data is, in this case is 10, right? And so the yellow is the neural network solution. And so you can see it's trying to match the noise. And the parameters are fairly far off, at least diffusion coefficient is. The proliferation rate's pretty similar. But now if you start reducing the data loss and trying to solve the PDE better, then you're going a bit away from the data, and you're now trying more closely matching the finite difference solution, and you're doing better, a little bit better in the parameters. But now here, when you go too far, make that data weight small, then you start to do worse in the data and the parameters again, right? Because you're not accounting for the data. And so where do you stop? What weight do you choose? That's problem dependent. There's a whole bunch of theories for how to do this best in PIN. We tried all of them and nothing really works. You always have this problem. And if you don't know the solution, which is the case in the problem you're interested in, you really have no idea how to choose this. Okay, but you can also use the BiLO approach to learn unknown functions. So for example, suppose the PDE depends on some function f. And what we can do is then use another neural network to approximate it. And then we want to learn the operator, the solution, as a function of these weights v that are parameterizing this at f, and w for the original weights. And so how can you do that? Well, the problem is v is high dimensional, right? Because it's another neural network. But there's a trick you can use. You can introduce an auxiliary variable. And so now your solution depends on this auxiliary variable z, for which when z equals f of x, you solve the PDE. And so now it's just like another parameter. So you can define a residual as a function of z, that's this guy. And then you can now take the derivative of the residual with respect to z, and now you're solving it around this guy. And so so you can do exactly the same thing as before. So all of this extra neural network is getting plugged into this variable z that's an input to your network. And so then you can introduce this auxiliary variable z and have this. And so now you have your residual now as a function here of this guy. And so the gradient is the gradients with respect to z. Your lower operator is exactly this guy, but the gradient has with respect to z. And so then this is the bilevel optimization problem you're solving when you do this. And so you can do it in a completely analogous way by determining trying to fit variable function. Okay. And so it just as an example, now if we want to calculate a variable diffusion coefficient, for example, we have to do some regularization. So we want to, if we want to solve this problem, and we want to, this is the ground truth, but we want to guess what that is. It's an ill-posed problem, so we have to regularize it a little bit. But now we can use it to use our BiLO to solve this problem. And here's an example. So again, this is the same idea as before. So we train it around just at d equals 1. But we train it, using the BiLO approach, so with a z. And so now what we do is we're going to vary the d. So here we're going to evaluate essentially our neural network at this new diffusion coefficient. And this is just a different constant. Okay, and then the solid is the BiLO solution, and the dashed is find a difference, so fairly close. And then the lower one is now evaluating at D2, but now D2 is variable, and then evaluating the finite difference, which is the dashed, and the BiLO, which is solid, and then they match very well. So now I can really vary the diffusion coefficient again in a local region. And it doesn't matter whether it's spatially dependent. Okay, and so then we can test this again like we did for pins before. So this is the pins at different data weights, and weight of 1, 10, and 100. And and so this is our ground truth solution, ground truth diffusion coefficient. And so this is predicting the pin solution. So really, you don't know which one you get. And then this is the BiLO. And so overall, you tend to do better. It's still, the data was kind of messy. I didn't show you the data, but the data is kind of noisy. So the solution is noisy. And you can see that because if I've now increased the data loss. And so the pins, the diffusion coefficient is going to be all over. Okay, and so now we can use that back into a patient-specific mathematical model, right? I go back and plug this in. So again, still the same imaging approach. And so now this is the pin data. This is the finite difference data. So now this is the pin data with 10 to the minus 2 as the weight. And this is the results between the pin and the BiLO. And so this is, what you can see is that here we've chosen a very specific value to match. But if you start going away from this value, you don't match very well. But this is our BiLO solution without having to match anything. So again, the dice is indicating that your neural network and finite difference solutions are matching the segmentations, how well they're matching in terms of the outer region, and then also the inner core. And so one thing to observe is, again, how well are you solving the compared to the finite difference method. And so both are doing a good job because we chose a particular 10 to the minus 5 choice, but this is a 5 times more accurate solution than that guy, but both are accurate in this case. So with that, basically, I want to close by saying, okay, we solved the PDE inverse, we reformulated the PDE inverse problem as a bi-level optimization. We have a stronger PDE constraint. It's more robust to noise. We can do the simultaneous gradient descent, which we even have some theory to indicate it works. And oops, and so sorry, and here we go. And we can get an efficient and fast algorithm. So let me stop here. I have another parts of the slide, but I'm not going to do it, which is how we can now do this for uncertainty quantification. But maybe I'll just give you the very quick idea. So in uncertainty quantification, now we have going to allow distributions of parameters. And so in the traditional approach for pins and other neural network type approaches, what's stochastic or variable would also be the weights. In our approach, it's the parameters that are variable, but not the weights, because we can use this lower optimization problem to determine the weights. And then, but as a they'll be variable, but only as a function of the variable parameters. And so instead of having a very large distribution of random variables, so it's much more efficient than regular pins. So, but let me stop and not go into that, and just hopefully you got the idea of how these things. Okay.
Questions?
In your this beam solution, you basically, rather than fitting the data, you actually fit it two numbers on threshold quantity, right?
Yes, only
It's
the
not the whole
threshold.
thing. Could you have done that whole thing fitting? Why not to do? And again, when you do that, and that also depends on weight, you said, how much is different in actual?
So so one of the things I think an interesting direction that we're thinking and planning to do is a coupled imaging PDE system. So where you're going to learn. So really, what you'd like to have is from on the imaging side, you'd like to have a map from your MRI data to cell density, and you can use the PDE to try to help you learn that map. The problem is with the MRI data you have, it's very limited. But maybe there's enough, the PDE can tell you which parts of the map are helpful, right? Which part of the images are helpful for that. And so we're thinking that there's a way of doing it in try to determine in terms of a coupled way, as opposed to just saying, okay, we segment and that's our data. In fact, there's more information, as you point out, in the data than just that segmentation. And so the question is, can we use the PDE to figure out if any of that is useful, how useful that is in predicting density? So yes, there's more information than what we're using.
Just related one more question. You haven't talked about the actual computation and timing and cost because of so many neural network addition stuff.
A little bit. So
better.
A little bit. So in terms of the GBM, so that was a full 3D problem. It takes like what did I say, a half hour or something like that or 1 hour to do one patient.
Compared to the standard finite.
Standard. So if you were doing Bayesian, it would be days.
Oh, I see.
That you could do that. So which is what we had tried to do before. It's faster if you do the adjoint methods, but you have to account for all the work you put into getting that to work, and then if you change the patient, you're in trouble. But ours, it just goes from one patient to the next without too much pre-training. We had a very quick way of pre-training the network, and people often don't account for that. Then the BiLO is a bit more expensive because we have now another parameter we have to differentiate. But the advantage is that it converges faster. So each calculation is a bit more expensive, but the convergence is faster. You don't need as many iterations.
Well, so patient to patient, you can pre-train the neural network, and same thing you can use for all patients almost?
No, so that's a good question. So you can. So if you train it on one patient, you can use that as a guess for the next patient. Then you can do better. We use some analysis actually to figure out better patient-specific pre-training. It's a little bit more expensive, but it makes the actual fine-tuning much faster. But you can do it just if you take the parameters from one patient and stick in another, but it's a bit long, it'll take a while to train the network doing it, to fine-tune the network doing that. But you can do better than that. And one of the things we'd like to do is figure out what are good ways to transfer the knowledge from one patient to the next. Like, what can you keep and what's different? Because they'll have different coefficient parameters, but they're not that different. Yeah, by a factor of 2 at the most. Yeah.
Which machine learning and neural network libraries did you use?
TensorFlow. I think this was mainly done with TensorFlow. Yeah. And we have some tutorials, and all the code is available, I think. So if you look in the paper, there's the GitHub site where the codes are available. But we have some tutorial codes using just the web browsers, the Google.
The notes, we're gonna thank John